Welcome back to Wood Engineering. I'm Jeff Rochko from Carleton University, and in this video we are going to continue discussion of beam design and talk about design for deflection limits. So deflection, unlike the bending strength that we were talking about previously, is a serviceability limit state, which means that we have different load combinations to consider than we did for the ultimate limit strengths. For example, bending strength and compression strength, parallel and perpendicular, were both ultimate limit states, which means limit states associated with failure. So for those, we had to factor up our loads to account for uncertainty in what the loads are. Now in serviceability, since we're talking a lot about comfort, occupant comfort, that occupants of our building or other structure aren't terrified to occupy those structures, we do not actually factor up our loads. So here is the serviceability limit state table. This is from the 086 standard, which is basically copied from the NBCC, the National Building Code. And you can see that all of the load factors for the principal loads are all 1.0, so they're not factored up. And we still add companion loads, but we do them with either 0.5 or 0.4. So when we're trying to calculate the deflections to compare our deflection limits against, we're going to use these loads, which are different than the loads that we use for calculating our strength criteria. And that is the table where we find those load combinations. So first I'm going to talk about what are the allowable limits for deflection, and then I'm going to give some indication about how to actually find deflections for our beams. So inside the 086 standard, there are some explicit deflection limitations. The first one is the allowable elastic deformation, which is kind of the most common regular kind of deflection limit that we're going to check. And that deflection has to be less than or equal to L divided by 180. That means our span length basically divided by 180. So if our span length is 2 meters, then we divide by 180, we get our deflection limitation in millimeters. And then we need to check that against what the actual deflection is. It also talks about modifying that limitation if there is a camber. So what it means when we talk about a camber is basically the beam is curved a little bit in order to combat the deflection that comes directly from dead load. So not just the dead load of the beam itself, obviously, but the dead load, whatever is on top from the floor level. So you would have a beam that looks, something like a very kind of shallow curve. And the whole point of doing this for a long span beam is that it allows us to actually have a more slender beam, because that beam can then take effectively more total deflection. So we camber it up here by approximately whatever my dead load deflection is going to be. And then that means, so under the dead load, it's going to basically go back to straight. And then I can use this L over 180. Instead of using it against my total loads, I can just look at L over 180 caused by just the other loads that are not dead load, live snow and wind, for example. So it basically allows my total deflection to be greater, which means my beam can be more slender. And if I do provide that camber, then basically I have a less stringent deflection requirement, because my deflection requirement is not on the total deflection anymore, but only on that deflection caused by live snow and wind, for example. Now, this is not really something that can be done with lumber, but with glulam, we can actually manage to get cambered glulam beams. So we fabricate them then with that slight inverted kind of deflected shape. Okay, so the other criteria in 086 is on permanent deflection. So this criteria says that if my long-term loads are more than half of my total loads, then so that means that most of my loads are coming from dead loads. A majority of the load is coming from dead load. Then I have a more stringent requirement of L over 360 for the deflections caused only by those dead loads. So then there are two different deflection checks that I would have to do. Okay, so when I actually go to calculate my deflections, which I can do using any method, I can use whatever methods I have from structural analysis. I can use a computer software to calculate my deflections, or there's actually tables of deflections for different situations in the handbook that are useful that you can also use. I need to use a specific modified Young's modulus of elasticity. So I don't just use E, I use ES, which is the regular E, which I would get from my tables, times KSEKT. Okay, where I have my specified modulus of elasticity that I get from my tables, which is the mean modulus of elasticity, not the EO5, and then my service condition factor for Young's modulus and my treatment factor, all of which I'm going to get from the appropriate tables that we've seen before when we talked about modification factors. And this accounts for the fact that stiffness is affected by moisture content, which we talked about when we talked about effects of moisture content. So since if my moisture content goes up, my wood basically becomes more flexible. I need to take that into account. If my wood is going to be in a wet service condition, it basically is going to increase my deflections. So where can I calculate my deflections? Well, I can go back to structural analysis. I can use virtual work, for example, to calculate my deflections. I could use moment area theorems. I could use the conjugate beam method. I could use a computer program, or I could use tables from the standard. So if I go to volume 2 of the standard, starting on page 927, not the standard, sorry, the wood design manual, then you can see that the CWC has provided in that manual a lot of helpful guidance for how to calculate deflection. So there's one method for calculating deflection that uses some factors based on loading condition. So if I have a simply supported beam and I have a certain load, then I can calculate this factor K, which allows me to directly calculate basically my deflection using that value from the table. But also there are the regular beam diagrams and formulae. So for example, for a simply supported beam with a uniform dead load, you can see here it provides a calculation for the deflection at the center. And you probably recognize this equation, 5WL to the 4 over 384 EI. For a simply supported beam with a uniform load, and they have beams with cantilevers, and they have beams with multiple spans. And so that's one easy way to come up with deflections for simple kind of conditions that you see all the time. So that's multiple ways to do it, and it's up to you basically how you calculate your deflections. And once I calculate them, of course, I need to compare them to the limits, these two limits that are provided in the standard.